Alright, today we're going to be talking about something called slope fields. Slope fields. And there's normally one or two problems on the AP exam that are involved with slope fields. They're not very difficult, but we do want to make sure we understand them. But before we get into slope fields, we're going to talk about how to solve a basic differential equation. And a differential equation is nothing more than an equation that has a derivative on one side and a function on the other. And the method that you want to use to solve these is called separation of variables. And essentially what you want to do is you want to get all of the x's on the right hand side and all of the y's on the left. So if there's a dy, you want to keep that on the left, put the dx to the other side, and we're going to solve that here. So we're going to start with the basic way you would solve any algebra equation is that you would do the inverse of both sides. So we see we have a derivative on the left hand side, and so to undo a derivative we do an antiderivative. So we're going to integrate this derivative dy dx, and if we do something to one side we have to do it to the other. So we're going to integrate sine of x as well. And anytime you integrate a derivative, it gets you back to the original function, y. And over here, we're going to integrate sine of x, which is going to give us negative cosine of x. But then we have to add this plus c here. And the reason is because there are an infinite number of equations that if you were to take the derivative of them, they would give you sine of x. You could have negative cosine of x plus 4, because the derivative of any constant is going to be 0. You could have negative cosine x plus 10 or plus 12. So you need to have this plus c. And the way you solve for the c is by using this initial condition right here, y of 0 equals 2. So essentially we have the ordered pair 0, 2. And we're going to use that to solve for c. So when y is 2, we have x being 0. And cosine of 0 is 1. So you end up getting 2 is equal to negative 1 plus c. Add 1 to both sides and you get c equals 3. And so now we know that our equation is y equals negative cosine of x plus 3. And that is how you solve a differential equation. Alright, so a slope field is nothing more than basically a plot of short line segments with slope. And so if you notice here, we have this differential equation dx dy equals 2y. And notice that the derivative here only depends on the letter y. Most of the slope fields that you're going to see are going to depend on both x and y, but this one particularly just depends on the letter y. So essentially, let's just say that, let's make a table here, when y is 0, so we'll call this y, and maybe we'll call this dy dx. Alright, and so when y is 0, you can see that dy dx is also 0. So if you go over to your slope field, what you want to do is you want to plot a short line segment that has a slope of 0. Actually, that looks a little bit more like has some slope to it. So slope of 0. So every time y is 0, we want the slope to be 0. So we just make a whole bunch of slope lines with 0. And now let's say when y is 1 that the slope will be 2, because you plug in 1, you get 2 times 1 is 2. So every time y is 1, we need a slope of 2. So you just kind of have to estimate here. It's not an exact science. These are just an estimate of the slopes. And so that's going to be about a slope of 2. And you can see that when y is 2, that the slope is going to be 4. Alright, so this one needs to be really steep. So maybe we'll make this one like that. And we'll make that kind of a slope of 4. Slope of 4, and okay, and you can see that the same thing works on the other side. So we'll do y equals equal to negative 1 and y equals negative 2, and you'll get a slope of negative 2 and negative 4. So this is going to be -2, -2, -2, and then really steep slope, -4. So basically what you have here is a picture of slope of the original function. So the original function is going to follow these slope lines, and it's kind of going to go through. If you can see here, it's going to kind of look something like this, or if it's going to be going down, it's going to look something like this. This is the basic slope field. Now if they give you a point to graph, which we do here in example 3, 0, -1, so now what we want to do is we want to actually draw a function that it's going to get close to these slope lines, and it's going to basically go through there like that. Alright, so essentially, actually let me redraw that again. So this is basically what the graph is going to look like. It's going to follow these lines, and I did it again. There we go. So that's basically what the graph is going to look like. And the cool thing here is you can actually graph these on your TI Nspire calculator, and I'm going to show you how to do that now. Alright, so if you got your calculator open, what you want to do is you want to go to the graphing screen, and if you hit Menu and Graph, you need to actually change the type of the graph that you're going to graph to differential equation. When you do that, you're going to get something here that looks a lot different than what you're used to. And so if you notice, remember ours was dy dx is equal to 2y, but you notice here that over here it's defined as y1 prime. So therefore you need to actually type in not 2y but 2y1. Alright, and that's going to give you a slope field. And actually, let's make our window match up with the one that's on our page. Our window on the page goes from -2 to 2, and we'll make this go from -2 to 2 as well. So it looks pretty much like what we have there, and that is what we have on our page. And if you actually want to see the particular solution, then you can actually make it go through a certain point, which would be example 3 on our notes. So let's say we want to go through 0 and -1, and you would specify that, and you can see now that this is the curve, whatever the curve is, that's the original function. It goes through the point 0, -1. Alright, so now we want to actually solve this same differential equation that we were using in the last couple examples. dy dx equals 2y. And this is why we started this video showing you how to solve differential equations, and so using separation of variables. Alright, and what we want to do is we want to see if the graph that we drew is consistent with the actual solution to this equation. So we want to separate the variables here, so we want to move the dx to the other side and the y to the left. So maybe we'll do it step by step here so that we don't get confused. So dy is equal to 2y dx, and I simply move the dx over there, and I'm going to divide both sides by y, divide by y, and so then maybe I'll separate this as 1 over y dy, and that's going to equal 2 dx. And then we want to solve this by taking the integral of both sides. Alright, so we want to integrate this side with respect to y, and we want to integrate this side with respect to x. And you'll remember from your table of integrals that the integral of 1 over y is just simply going to be the natural log of the absolute value of y. And the integral of 2 is just going to be 2x, but you actually need a plus c. Now let me mention something here. Technically, you need a plus c on this side as well. So let me just put that, maybe I'll make that c1 and I'll make that c2. Alright? Because anytime you're integrating without a lower and upper limit, you actually need a plus c. But, and this is the only time I'm going to do this, if I subtract this C1 from this side and subtract it from that side, put C1, then it cancels here and you have C2 minus C1, which is basically another constant. And so this constant that's on this side is basically combined with the constant that's on the other side, so that really what you have here is natural log of the absolute value of y is equal to 2x plus, we'll just call it some constant. All right. So if you remember from pre-cal, we want to solve this for y. So the base on the natural log is e. So if we do this little around the world thing where we convert it from log to exponential, we're going to take e and raise it to the other side and set it equal to y. So let's do that. E to the 2x plus c is equal to the absolute value of y. All right, now there's this little step here that you want to get really, really comfortable with. If you remember, one of the properties of an integral, or excuse me, of exponents rather, is that if you have the same base, let's say x to the 4th and x to the 6th, you're adding your exponents. So that's going to be x to the 4 plus 6. Well, it works the same way backwards. If I have x to the 4 plus 6, I can actually break that down into x to the 4th times x to the 6th, because we know that we're adding exponents. So over here, we can actually break this down into e to the 2x times e to the c. All right, and so that's true because you're adding exponents. Now, e, we know, is nothing but a number. That's 2.718. So if you're raising a number, 2.718, to a constant, guess what? That is going to combine into one big constant. So you're going to have c e to the 2x equals the absolute value of y. And I will take off the absolute value, and essentially our general solution is going to be plus or minus c e to the 2x. This is called a general solution. General solution has a c in it, and in order to get rid of that c, we need a initial value. So if you remember, our initial value was 0, -1, and so we want to use that to get our c. So when y is -1, x is 0, so basically you have c e to the 2 times 0. So e to the 0 is simply 1, so c is equal to -1. All right, so if c is -1, now we can go back here and write our particular solution. And our particular solution is going to be y equals negative e to the 2x. And if we remember, e to the x is an exponential growth function, so this is actually going to be a reflected exponential growth. So in green, maybe I'll draw the original exponential function, and our function is the reflection of that, which is the blue curve, which is basically the same as what the calculator gave us and what we drew by hand as well. So that's how you solve differential equations, by separating the variables. Alright, so now we're going to sketch a slope field, and as I said earlier, most of the slope fields that you're going to be dealing with are dependent upon x and y, and then we're going to check it on our calculator. So you see here we have several ordered pairs represented by these red dots here. So maybe we'll make a table, and in this table we'll have 3 columns. We'll have x, we'll have y, and we'll have dy dx. And we'll just pick basically random ordered pairs, and we'll see what slope we get. And when we get those slopes, we'll sketch them on the graph. So let's just start with the origin, 0, 0. All right, well, when x is 0, you can plug it in here. When y is 0, you get a slope of 0. All right, and then we'll go to 1, 0, and 2, 0, and we'll just do a whole bunch of different ordered pairs here. When 1 is 0, so when x is 1, you have 2 times 1 minus the y is 0, so you have a slope of 2. When x is 2, you have 2 times 2 minus 0, so the slope is 4. Alright, and let's see what else we'll do. We'll do maybe the whole first quadrant, 1, 1. When x is 1, you get 1 for the slope after you plug in y is equal to 1. And then we'll do 1, 2. Alright, when x is 1, you got that. And when y is 2, you're going to end up getting 2 minus 2, which is 0. And let's see, let's keep going here. And we'll do 0, 1. We'll do 0, 2. We'll do 2, 1. And we'll do 2, 2. Alright, when x is 0 and y is 1, you get 2 times 0 minus 1, so negative 1. And here would be negative 2. Okay, when x is 2 and y is 1, let's see what we get. 2 times 2 minus 1 is 4, minus 1 is 3. And then the last one is going to be 2 times 2 minus 2, so 4 minus 2 is 2. Alright, so basically now what we want to do is we want to sketch these slopes at these different points. So at 0, 0 we have a slope of 0. And then at 1, 0 we have a slope of 2. So maybe we'll make that our slope of 2. And then at 2, 0 we have a slope of 4, so that needs to be much steeper. And at 1, 1 we have a slope of 1, so that's going to be not as steep, so we'll make that like that. And at 1, 2 we have a slope of 0, so at 1, 2 we have a slope of 0 again, so that's going to be flat. And at 0, 1 we have a slope of negative 1, so it's going to be like that. And at 0, 2 we have a slope of negative 2, so it's going to be a little steeper than that, so maybe something like that. And at 2, 1 there's a slope of 3, so 2, 1 is a slope of 3, so that needs to be kind of steep. There we go. And at 2, 2 is a slope of 2, so we'll call that slope of 2. Alright, and you can do the other quadrants on your own. You can see the idea. So now we're going to check it on our calculator, and we're actually going to make it go through the point 0, 0. Alright, you can see we're here back on our calculator, and we are going to let the calculator sketch the graph of dy dx equals 2x minus y. So you go to your menu, you need to change the type of graph that you're going to do to a differential equation. And so we're going to do 2x minus y1, and we're going to hit enter, and we're actually going to change the window to match the window that we have as well. So we'll make it go maybe from negative 2 to 2, and again from negative 2 to 2. And you can see that that is the, looks like the curve is looking something like this. And if we really want to see the curve and where it's going through, we will actually give it an initial condition. Maybe we'll say 0, 0. So if we go back and hit Control G and pull this up, we'll go back here and we'll give it an initial condition of 0, 0. And now we can see the graph going through here. And so that is the original graph, the original equation of the graph. Alright, so this next example, we need to be able to match up 4 different differential equations with the proper slope field. Alright, so there is really not a definite science to this. This is just kind of trial and error. You have to kind of look at it and try different points and kind of see which ones make sense. There are some general rules here. So for instance, maybe we'll start with number 4, because that looks like it would be the easiest one. Notice here that one of the rules in math, you cannot divide by 0. So we see here that at the very beginning, x cannot be 0. Alright, or you'd be violating one of the rules of math. So you're looking at the different graphs, you're saying, okay, It's not this because we see that there's some slopes when x is 0. Here there's some slopes when x is 0. Here there's some slopes when x is 0. So number 4 must be C. If you notice here that there is a section here that does not have any slope values at all for when x is 0. So the answer for number 4 would simply be C. All right, so let's go to maybe we'll go to number 3 next, and we'll say that when x is, let's say, 3 and y is 0, we notice that you can't divide by 0, but actually a number over 0 really equals infinity. All right, so if you notice here that for various values of x, when y is 0, you get an infinite slope. And we know that lines that have infinite slope are vertical lines. Lines that have 0 slope are horizontal lines. So essentially, what are we looking for? We're looking for a graph that when y is 0, you have vertical lines. So you're looking around here and you're saying, okay, here would be the most obvious graph here. If you notice that all these different y values here, maybe we'll use a highlighter, for all these different y values equaling 0, you have vertical lines which represents an infinite number of infinite slope. So this one would be A. All right, and then we'll look at maybe number 2, and here we will say that when x is 0, the slope is 0, so we'll say y prime is 0, and when y is 0, y prime is also 0. So basically you're looking for a graph that when x is 0, you have horizontal lines which represent a 0 slope, and when y is 0, you're looking for also that same thing. So if you look over here, very clearly when x is 0, which represents the y-axis, you have a bunch of horizontal lines which represent 0 slopes. And if you look at the x-axis also, all right, you'll see that the slopes are approaching 0 there also. All right, so that one is going to be D, and by default this would be B. And if you want to work through B, you can. You can basically see the idea here is that when x and y equal the same number, the slope is going to be 0. All right, so you're looking for a graph where, let's say, when x is 2 and y is 2, you have a slope of 0. Or let's just say, let's use 3 and 3 instead. And so you can see that maybe this point right here represents 2, 2 or 3, 3, and you have a 0 slope. So this is going to be B. And we got 2 more problems here. These are going to take us no time at all. We want to solve these differential equations, and they give you initial value. So this first one, dy dx, is equal to 2e to the x minus cosine of x given 0, 3. Technically, you're supposed to move the dx to the other side so that all the x's are on the right and all the y's are on the left. But this one's easy enough where the x's are already all on the right, so we're just going to integrate both sides here. So we're going to integrate that side, we're going to integrate that side. If you integrate this side, you're going to get y. If you integrate this side, well, the nice thing about the integral of e to the x is just e to the x. So it's going to be 2e to the x. And the integral of cosine is sine, but there's a negative in front of that. So it's going to be negative sine of x. And remember, you need a plus c after this because this is called an indefinite integral. When you don't have a numerical lower or upper limit, you always need a plus c. And the way you get rid of that c is by plugging in the initial value, 0, 3. So when y is 3 and x is 0, we will be able to get the letter c. So e to the 0 is 1 times 2, so we have 3 is equal to 2, sine of 0 is 0, and so we can see that c equals 1. And don't forget, this is called your general solution. All right, and what we're finding is the particular solution. And so our particular solution is going to be y equals 2e to the x minus sine of x plus 1. And that is the differential equation that we get. That's the solution. All right, let's do this one over here. And we want to integrate both sides once again. So we integrate that, integrate that. So integral of dy dx is simply y. And we recognize that the integral of the secant squared is tangent. So that's going to be 5 tangent of x. And then we have to integrate this. So we're going to change this maybe to x to the 1/2. And when we integrate x to the 1/2, we end up getting x to the 3/2 divided by 3/2. And we have a 3/2 there. So that's just going to cancel. Or you could think of it as dividing by 3/2 is the same as multiplying by 2/3. So that's going to cancel out. All right, and we also need a plus c again. So we can plug in our 0, 7. So when y is 7, we end up getting 5 times the tangent of 0 minus 0 to the 3/2, and that enables us to find c. Tangent of 0 is 0 times 5 is 0, so c equals 7. So then our final answer is y equals 5 tangent of x minus x to the 3/2 plus 7. And that is the solution to that differential equation. All right. So if there's anything else that's not on this video, you can look at the notes on the website, and we'll practice this in class tomorrow.